All right, off we go. All right, this is going to be a slightly different kind of lecture than we've had uh, up to now, as you'll see. But it's about a very basic problem involving pretty simple parts. These are all logical satisfiability problems. So, all right, so everything today will be about just simple Boolean logic, which we've seen a little bit before. Okay, so we only have like three operations. Okay, so all the variables are true or false, or sometimes represented as 1 or 0, 1 for true, 0 for false. And we only have three operations. One is the logical and, or the conjunction. So true and true is true, but true and false is false, right? False and false is false. The other is or. The fancy name is disjunction. So here, true or true is true, true or false is true, false or false is false. I'm guessing we all know this. And then the third one is negation or not. Not true is false, not false is true, right? It's just about composing these things, and you could put parentheses around things to make them more complicated. Okay, so for example, just to make sure we're on the same page, yeah, I don't know, poor Boole, his name is actually spelled Boole, and forever, like every programming language misspells it. Okay. Anyway, all right. So just to make sure we're on the same page, what might be a Boolean formula to express the exclusive or? So that means that you're given two variables, x1 and x2, and I want to evaluate the exclusive or. So exclusive or means that true true evaluates to false, and false false evaluates to true. It only evaluates the false false evaluates to false. You only get true if it's true and false or false and true, right? So exclusively one or the other. All right. How might we write that as some composition of these simple things? Yeah. Yeah, x1 or not x2 or x, yeah, assume that's roughly a truth table, right? We're kind of enumerating the two possibilities that output true. So if x1 is true and x2 is false, then that first clause, sometimes what's wrapped in a parentheses called a clause, will evaluate the true, and then the other one goes over the other case. Okay. All right. Now, for every one of these Boolean formulas, you can also imagine it as like a tree, right? So for exclusive or, you can kind of imagine a tree that starts with the variables down at the bottom and the logic kind of moves up. You've sort of seen this briefly when we discussed circuits. This is even a special case. Okay, I think we're on the same page. Here's something a little more complicated that took me a little while to figure out. So suppose I want to sort of like simulate adding 2 bits. Okay, so this is takes 4 variables, x1, x2, x3, and x4. And I want to imagine adding x1 and x2 at just 0 or 1 type numbers, and that returns a 2-digit number x3 or 2-bit number x3, x4. Okay, so this formula should return true if and only if x1 plus x2 is equal to that 2-bit number described by x3, x4. Okay. It took me a while to figure this out. I'm only mildly sure it's correct. Okay. Still, whatever. As a tree, it's a little bigger than XOR. Okay, but otherwise it still has that tree-like structure. So the subtrees are correspond to matching parentheses in the formulas. So your sub-parentheses correspond to subtrees. All right. So, all right. So those are nice examples. Now, all right. So at some level, ors, ands, and nots seem somewhat limited. They can only do so much. But with some imagination, they can be kind of more expressive as well. So at some level, we can think of trying to invent sort of a programming language of some kind, starting with just and, ors, and nots, right? So right now I know how to express those three things, but suppose I wanted to express something that's sort of like assignment. Z equals X, right? So at some level I want to come up with a formula that'll be true if Z is equal to X and false if Z is not equal to X. It's sort of like saying Z has to be equal to X. It's sort of like an assignment. Okay. Anyone want to take a stab at that? Yeah. Yeah, okay. Z and X or not Z and not X, right? So the first one is saying they're both true or they're both false. There's only two possibilities. Okay, here's one that's maybe a little bit more elaborate. What else do we use in program? If-else statements, right? So I want to produce a nice short formula. It's going to be a little bit more involved, but not too much, such that if X is true, it'll return the value of Y. Otherwise, it'll return the value of Z. Okay. If X, then Y, else Z. Does anyone want to try that one? A third variable. So there's three Boolean variables here, as opposed to two, as in the previous examples. You might need some scratch paper. I did, at least.
X and Y for negation of X and Z.
X and Y, or negation of X, sorry, I should parentheses around, X, negation of X and Z. Okay, so what's the logic here, right? At some level, the first X in the beginning of each clause is sort of like a gate or a switch, right? So if X is true, then that first clause, well, if X is true, then the second clause is automatically failed. Some of it was kind of like ignored. So it'll return true if and only if Y is true, if we want. And if X is false, then the first clause will always fail. And the second clause, you get past it, not X, so it'll return true if and only if Z is true. Okay, so I think that's exactly what I had. That's right, okay. So either X is equal to 1 and Y is equal to 1, or X is equal to 0 and Z is equal to 1. Okay, so those are just like two simple examples, but you can imagine starting to put together like really basic things, just like one level beyond and or, right? To be able to do things like assignment and be able to do like if-else statements. We did addition to some extent on the previous slide, right? So now things are starting to come together. You can compose them. You could put one inside the other, right? So the takeaway is that Boolean algebra is actually pretty expressive, even though it's so simple. Okay. Some level you might know this intuitively, since in principle everything on a computer should boil down to Boolean logic, and you're ultimately able to do pretty sophisticated things. All right. So here's the problem we're interested in. So you're given as input some kind of Boolean formula over like n variables. So I'll give you like that full equation with lots of parentheses and stuff like that. And we'll refer to like the total size of the formula just being like, the total number of symbols that are written down. Okay, so that's like roughly the number of variables with repetition as they occur in the formula. That's your input size. And so I give you a formula and I ask you, does there exist some choice of x1, x2, x3 through xn to make the formula output true? Is there some way to quote unquote satisfy the formula? Okay. So I have an example. So here's a formula with just two variables. Okay. My question to you is that formula satisfiable?
It's not satisfied.
Okay, who thinks no? Who thinks yes? You think yes? Okay, why not? Or, well, at least the why not. Okay, but why no?
Because there's x1 and negation of x1. So if you try to add them, it's always not a situation where you won't have satisfied.
Yeah, okay, so this is a conjunction, and I've actually enumerated all four possibilities of x1 or not x1, and then x2 or not x2. So somewhere there'll always be a contradiction. You can't satisfy all four. Okay, so I chose a particular example where you can actually see and know clearly that the answer is no, but in general, it's actually not obvious how to prove something is no, unless you have something obvious like that going on. All right. On the other hand, if the answer is yes, it's actually easy okay. So this happens to be an example where we can see why it's no, right? And it's not generally true that it's easy to see why it's no because there's so many. How do you know you eliminate all possibilities? On the other hand, if the answer was yes, how could you kind of easily prove that the answer is yes? If there was a satisfying solution, what would be a proof? Yeah.
Just plug them in.
Just plug them in, right? So whatever values of x1 through xn make it satisfied, that actually is a simple proof. I can plug it in. It's easy to evaluate the thing. I'm sure you can all write the code to evaluate a Boolean formula. It runs. It should be able to do in linear time. And so there's always a proof for a yes answer. Okay. And so that's actually makes it part of a slightly more general class of problems, what's called kind of an abstract search problem, because we're kind of searching for a satisfying assignment. But the key point is if we find it, we can recognize it. Okay, so like if you do find a satisfying assignment, you can very quickly just evaluate and double check it is a satisfying assignment. Okay, sometimes so the definition of a search problem in this sense is some problem where you're looking for an answer, but you can recognize the answer if you do find it. Okay. Not all problems have this format, although most problems do. Usually usually we look for things that we can recognize, but that's not always the case. Okay. All right. So this is an example of a search problem, and that means that there's always one kind of very simple algorithm that's possible. So maybe I'll ask you guys, if you're worried about Boolean satisfiability, you're looking for a satisfying assignment or something. What are some ideas for algorithms? Or what is a silly idea? Don't worry about running time. Something that'll definitely work. You can plug in all the possibilities and try everything, right? Because the point is that you can guess some choice of X and then you can verify if it works or not. I can compute f of X. And so search problems have this nature that I can at least enumerate all the possibilities and see if I recognize that as a solution, recognize that as a solution, recognize that as a solution, recognize that as a solution. So SAT is sort of a prototypical search problem that allows for brute force, enumerative approaches. Okay, but on the other hand, if I compare it to, from lecture one, we talked about the over-under game, right? Where I'm searching for a number between 1 and 100 or something. That's also a search problem in the sense that we can recognize it when we find it. But it seems like SAT is harder than over-under. Because over-under had this nice structure. I can always divide the possibilities by half. But somehow SAT, at least directly, it's hard to see there is such a nice structure. I mean, over-under we could do in second grade or something. I don't think second graders can come up with a good algorithm for satisfiability. Okay. All right, but they're still both search problems. What's the difference? Is at some level the question. All right, so the big question, one of the biggest questions out there, is whether there is a polynomial time algorithm for this problem. Can we, in polynomial time, decide if there's a satisfying solution or not? Okay. It's a relatively simple problem. Okay, so I thought I'd take a vote. Okay, so your choices are yes, no, or you're not going to vote. So who's not going to vote? Oh, a lot of you. Okay. All right. Who thinks that there is a polynomial time algorithm? Okay, I think there's like 10 of you. And then who doesn't think there's going to be a polynomial time algorithm? Okay, it's like, okay. Who regrets not voting? Okay, one. And then the rest of you should be ashamed. Okay, all right. So for those who said yes, what are some maybe ideas or approaches to trying to solve this thing in polynomial time? Any ideas fine, it's just for fun to, yeah.
We can try to like put it into a tree like we just did.
Okay.
And look for the rules and then see if either side.
Okay, so you have the tree, fine. And then I can look for,
And then we can try to solve the tree somehow. Not sure.
yeah, I mean, can I like, I don't know, focus on this subtree first or something and not the other subtree? Maybe that's sort of a high level idea. One thing I want to point out is that a variable like x1 can be in both of your subtrees, right? So if you just kind of focus on roughly half the formula, it does impact the second half, right? So that makes it tough, right? So it's hard to divide up the formulas because those variables can be all over the place, which kind of connects what would seem to be far parts of the tree in some sense, right? The logic doesn't necessarily separate out so cleanly. Any other fun ideas?
Can you convert the tree to be like with and statements so that you just say that one side is false and then say that it's not.
Well, yeah, so what if I told you this was an and up top?
Yes, we just focus on one of the subtrees.
Okay. Uh, Fine. But then the next subtree might be an or, and now we.
Try to convert the problem into only and. Yeah.
Okay. So, okay. All right. So you can do things like this. So let's say you have something like A or B, and this is actually a good idea. Okay. Now there's this what you call it, De Morgan's laws, right? That let you take an and of ors and turn it into like an or of ands, or something like that. Oh, do we want to do the opposite here? Okay. We want to do the opposite. So we have something like A and B or C and D, right? And so this is hard, right? Because the or is in the middle and you want to make it like an and of ors instead. Okay, so what might that look like? What does this become if I applied De Morgan's laws?
Not A or not B.
Sorry?
Not A or not B.
Not A or not B? Is that what? Okay. Not C or not D? Uh, Wait, what? Is this true? Wait, did you just make stuff up on the second? Okay. Uh, Sorry?
Take a note of that whole explanation. I think that's
Okay, but we're not taking a not, right? We're distributing the or of the ands. Uh, sorry? I apply what? Okay, just tell me what to write. What should I write here? If I want to turn this into, right now this is an or of ands. We want to turn it into an and of ors. Okay. A or C and A or D, B or C, and B or D. Okay, is that correct? Right, so this is true if either both A and B are true or both C and D are true. That seems to be the case, right? Because in each of those four, it has an A or a B, so one of A. Yeah, okay, so that's okay. Okay, I think this is right because if for example you had like true, false, this should evaluate to false, right? And in particular, we can look at we can look at the clause that has B and D in it. So that's this one, and that will give you the false. Okay, good. All right, so what happened? I took an or of two ands, and it turned into an and of four ors. Okay, so presumably I could do that, and now this one is kind of pretty easy to evaluate, right? Because this says, well, this might be easier or something, right? Now, okay, that's an idea. Now, but one thing maybe to keep an eye on is that while this might seem innocuous for a small formula, we did double the size. Okay, and if I start doing that to a really deep tree, right? Imagine this gets really deep, right? And it's kind of alternating ors and ands, and if every time I do this trick, I'm doubling the size and doubling the size and doubling the size every time I go down one level, then it's going to grow exponentially big. So this actually, the Morgan's law kind of thing, to flatten it out, will actually increase the size so much that even if you get it into this form, and you can do that in polynomial time, that won't give you a polynomial time algorithm on the original input because you're running it on something that's so much bigger. But otherwise, it's a good idea. This is actually an exercise in this chapter. All right. Any other fun ideas? Yeah. Okay. Yes, in general, I have an or at the root, and then can I just like focus on this or that? I mean, yes, but then, well, okay, so this sort of came up. What happens though? Okay, now the next level you have an and. Uh, okay, so here's maybe, okay, here's maybe one thing to keep track of. So let's see if I can do this. All right, here's an and of ors of various other things, right? And you say, okay, can I just focus, whenever I have an or, can I focus on one subtree over the other? And well, okay, so one reason this at least gets a little bit tricky is that now, okay, so here I have sort of four subtrees, right? And for each case, for each of those pairs, I would maybe focus on one or the other, okay? But like choosing to focus on this one affects whether you should focus on this one or this one and stuff like that. So there's still some combinatorial. It is true that if you focus on this one, then you don't have to focus on the immediate sibling, but it still has interactions with the other because they could be sharing variables under the hood. So it doesn't quite separate things out so easily and make it trivial, if that answers your question. Okay. All right. For those who said no, what was some of their intuition? Yeah.
So if I have a tree like this in which the whole subtree is only on one side, so there's nothing on the other side, then I think we have to plug in all the values, right? There's no other way to compute.
Have to plug in all. Well, so even if you're saying like, oh, I have something like this, and this side is like basically trivial, and everything's interesting down here.
And that stays the same. So it's only a one-sided tree.
Uh,
All the subtrees are always on the left side.
like this. Would that be even a very interesting formula?
I mean, so we will have, let's say, x1 or x2, and then on top of that we have some, let's say, x1 or x2 and x3, and then on top of that we have, let's say, 4 x4 and so on.
Okay, well, okay, so you said if we have x1 or x2
In bracket,
in brackets
let's say,
and
and x3,
x3,
and then another bracket, and then something else, and we continue. And wouldn't it be the case that we have to plug in all the values?
would it be the case they have to plug in all the values? Uh, well, I think, well, at least this formula seems very easy because I would just set everything to be true.
Yeah,
So I wouldn't have to plug in all the values. All right. Anyone else who said no, what was some of their intuition? Yeah, from first principles. Okay, so if you divide it in half, it just seems complicated, I think is what you're saying. Uh-huh. That's good, right? Like merge sort, I mean, lots of divide and conquer algorithms split in half.
yeah, but when you split in half, there is dependencies between the half.
Yeah, there is dependencies between the half. But well, the suggestion that was said was something like, oh, do you get a recursion that looks like T of n is equal to 2Tn over 2 or something, right? But that recursion itself is not bad, right? Because that's what merge sort looks like. Well, okay, so I tried putting together, I thought about this. So a pros and cons list for reasons why we might expect in algorithms and reasons why we might not. This is just, whatever I thought of. It's not like an official thing, right? So I think the main argument pro is that Boolean logic is very simple. And it's like made for computers, right? I can imagine running computers to simulate a formula. Like this is exactly what computers should be good at, like Boolean logic. It's like the only thing it can do, right? And as already noted, it's easy to evaluate Boolean functions. So I think those are good, like pros, right? At some level, it seems simple. Okay. But cons, why would I be skeptical of the existence of any algorithm? I think for me, the biggest reason is that Boolean logic is very expressive. It's almost like a universal language, right? We did the if-else statements earlier. We did assignment earlier. You can imagine making a whole programming language out of these ands and ors, right? So in other words, these Boolean formulas in our examples, they all seem very simple and stuff because that's the only thing I can write down. But potentially they can express like entire complex programming languages, right? I don't know. Microsoft Word is a big Boolean formula or something, right? And uh, and the idea that I could take anything, or suppose I had an algorithm, right? Then we're saying that any question I can pose logically, and I can come up with a formula for, we can get an answer for it, right? So if I could like figure out how to express a cure for cancer as a logical formula, We could plug in this algorithm, and if it's not too slow, we could cure cancer, I guess, right? But the point is, at some level, is it too good to be true to get an algorithm for this? Because Boolean logic is quite expressive. It might be cumbersome, right? But it is expressive. So in fact, we do not know if there's a polynomial time algorithm or not for this problem, but people still work on it. People also work on heuristics for it, where they don't have guarantees, but sometimes it gets lucky. All right, so if we don't have an attack on this very general problem, trying to satisfy Boolean formulas, right? What's an alternative, right? We don't just give up. Okay, we can think about special cases about this problem, right? If this problem is too general, then maybe there's special cases of Boolean formulas that we can solve and might still be useful. So we're going to explore that question. All right, so that brings us to formulas that are in what's called conjunctive normal form. Okay, so that means it's an and of ors, but it's not like arbitrarily nested. It's just like one and with lots of ors. Okay, so as a tree, it's going to be pretty flat. Okay, one big and at the root, and just a bunch of ors over variables. Okay. All right, so this is just a special case of Boolean formulas. It's like a nice, clean case. It's even easier to evaluate these because you don't have to really worry about recursing down nested parentheses and stuff. Okay. All right, so that's called conjunctive normal form. And so the question is, given a Boolean formula f that's in conjunctive normal form, can you decide if there's a satisfying solution? Same question as before, but to the special case of formulas in conjunctive normal form. All right, I can take the same poll again. Who thinks that for this easier case, special case, we might come up with an algorithm? Oh, who's not voting? Okay, 5 of you guys. All right, who thinks we can come up with an algorithm for this case? Okay, I would say that's a little more than majority. And who is still skeptical that we can solve even this special case? Okay, as usual, doesn't quite add up. That's okay. All right. Okay. So, right. Okay, so that's that more modest question. Now, okay. So previously we talked about how if you just have any Boolean formulas, you can easily express, complicated thoughts like assignment and if-else statements. Okay. But those formulas we came up with weren't necessarily in conjunctive normal form, right? Like take z equal to x. That's the opposite. That's actually called disjunctive normal form because it's an or of ands. It's not an and of ors, right? Okay. But can we turn this into CNF form? Yes? Okay, what should I write down? How do I do this?
We could just negate the whole thing, and then where is it?
You want to negate the whole thing? If you negate the whole thing, then you'll get the statement z is not equal to x. It is true that if you negate the whole thing, that'll flip the ands and the ors around. I agree with that, and you'll get conjunctive normal form. But you'll no longer be expressing z equals x. You'll be expressing z not equal to x, because that's a negation of z equals x, right? Can you express z equals x in conjunctive normal form?
Can't we just renegate it and then will for it?
So if you negate twice, you'll get the same thing, right? Two negations, they just cancel out.
No, like solve the whole thing and then once you have your result.
Oh, I think you'll just figure out if a formula is unsatisfiable. But you want to know if it's satisfiable. It could be unsatisfiable and satisfiable. It's not like one's exclusive of the other. Yeah. So how do I write assignment in conjunctive normal form?
Z or X bar and X or Z
Z or X bar.
and Z bar or X.
Okay. Did you just guess that or did you derive that or?
Just a De Morgan.
Huh?
Just a De Morgan's law.
Okay, yeah, so we can take this more slowly. So if we do that De Morgan's law from before, right, you're going to get, well, I guess I did it really slowly. I did one variable at a time. Okay, oops. All right, so De Morgan's law is it 2 steps down or whatever. Is that even De Morgan's law? I don't care. Okay, anyway, so you can do the usual Boolean algebra type of stuff. That gets me to the third line. 2 of those clauses are like silly, right? Like X or not X is always satisfied. Z or not Z is always satisfied. So we delete those 2, and we'll get Z or not X and X or not Z. Okay, so while conjunctive normal form is somewhat restrictive, it's not so restrictive that we can't figure out how to do assignment with constant size. Okay. All right, how about if-else statements? Can we do if-else statements in conjunctive normal form? We do the same thing, right? Okay, so there's the first thing, or whatever. This thing makes it a little bigger, and I guess this line is redundant, and you get something like that. Okay, which is I feel like a little hard to guess originally, but it doesn't matter. Okay, the point is that you can express if-else statements also in conjunctive normal form. Okay, so actually, CNF maybe is also pretty expressive, the same way that Boolean formulas were, right? So, yeah, at some level, I tried putting together another pros and cons list to answer this kind of questions. It's roughly in line as last time. CNF formulas are even simpler than Boolean formulas. That gives us some hope, and it's even easier to evaluate them. That's the good news. On the other hand, they're still pretty expressive, right? We can still do assignment. We can still do if-else statements. Maybe we can do some other stuff. Are they even universal? I'm not as sure about that compared to Boolean formulas, right? And, is it too good to be true? I'm not as confident about that compared to before, a priori, right? Because it is limited. All right, so similar question, but of course, by restricting it, the cons become a little bit weaker than before. Okay, so can you hear me? Okay, so we don't know the answer to this question either, in the sense that we don't have a polynomial time algorithm. We don't have any proof that there isn't one. Okay. All right. But it does get a little bit interesting. I realize up to this point, maybe it's been a bit of a disappointing lecture. Okay, so here's what we do know. We do know that if there's a polynomial time algorithm for CNF SAT, then there's a polynomial time algorithm for Boolean SAT. Okay, so obviously if there's an algorithm for Boolean SAT, then you get a polynomial time algorithm for CNF SAT because that's a special case. The interesting one is the opposite direction, right? And this is also kind of an interesting way to go about these questions. We have 2 high-level questions that are interesting, of practical interest, simple to state. We love to be able to solve these things. We can't really answer them directly, but we were able to actually relate them, right? Somehow they're kind of like tied, right? So this at least gives you an interesting statement about CNF SAT, right? If you thought that maybe CNF SAT was going to be easier because it's so much more restrictive, maybe not. Right? Because apparently solving CNF SAT is tantamount to solving Boolean SAT, which maybe you're more comfortable with admitting is going to be pretty tough.
Also, doesn't the
Yeah, exactly. So we didn't actually answer the original questions of, can I get an algorithm for either of those problems? But we know that the answer is the same for both questions simultaneously. If you get an algorithm for one, you'll get an algorithm for the other.
So are we saying that every Boolean formula can be converted into CNN?
That's exactly, okay. Yeah, so at some level, okay, good. So obviously, because one direction of this theorem is obvious, because Boolean is clearly more general than CNF. So, this is your only guys, I mean, yeah, I thought I'd at least ask you guys, how do you argue the interesting direction? How would you argue that an algorithm for CNF SAT gives you an algorithm for Boolean SAT? How do you make that argument?
Can we say any Boolean set can be expressed by CNF?
Right. So if I can show that any Boolean formula can be converted to CNF form without increasing the size too much, right? If I took some formula that was like size n and turned it into size 2 to the n or something, that wouldn't be as good because running a polynomial time size thing on an exponential size thing is an exponential size time algorithm overall. But if I can take my Boolean formula of size m and make it like m squared or just some polynomial of m, then the polynomial time algorithm on that CNF will still give a polynomial time algorithm on the original thing. Okay, so here's what we're really going to prove. We're going to give a polynomial time algorithm that, given a Boolean formula f, will produce a CNF formula g. Okay, this formula actually has more variables than before. It can have more variables. It has roughly the same size. All that matters is the size within a polynomial, but actually will only go up by a constant factor, such that our original formula is satisfiable if and only if that new CNF formula is satisfiable. Okay, so we can actually make a CNF of the same size, roughly up to constants, while preserving satisfiability. So if you can solve CNF, you can just take a Boolean formula, build out the CNF, and then solve the CNF. Okay, so this is called a reduction. Reduce one problem to another and thereby show they're equivalent. At some level, this past homework, all those graph algorithms are also reductions, right? I give you variations of shortest path algorithms and you reduce it to more standard shortest path algorithms. Okay. All right, so I drew this one as an example. This is the addition one from before because it's big enough to be interesting. Okay, any ideas before I reveal the tricks as to how to do this? How do I turn this Boolean formula into conjunctive normal form? So it needs to be a flat tree. Right now it's a deep tree. And just applying De Morgan's law, as we know, or whatever that distributed stuff, won't work because that will actually blow up the size. So you can't just do this and of ors becomes ors of ands. Do more clever than that. You can introduce variables though and stuff like that. You have that at your disposal. All right, let me make it a little bit easier. As a pre-processing step, like note that this one has 4 children, right? 4 variables. But it's easy to take that into an and of 4 variables and make it into an and of 2 variables each, right? So suppose as a pre-processing step, I just convert it into like a binary Boolean formula, so to speak, which just has kind of 2 variables involved or 2 subtrees involved. Okay, so now that we can assume the tree always has 2 children or 1 children, no kind of wide things, just to make it easier. All right, so we have this form. All right, any ideas for this? Any fun ideas? They don't have to be correct. Yeah.
Replace one of the logic gates with a new variable.
Okay. So let's take this one. So I'll make a variable. I'll call it z1. Okay. So how would I replace it? Sorry. Okay. I can write. I can write like z1 is equal to x1 and x2 in some way, right? I can write down whatever that converts to, right? So that just becomes like an extra thing. So at some level, I kind of rip this off. Oops, what am I doing? Right? I rip off the tree and I say, okay, z1 needs to be equal to whatever this tiny little thing evaluates to. And then I'll kind of drop that in there, right? And we can do this from like kind of in a bottom-up fashion. So I can take out this other subtree, this and of x3 and x4, and say I'll add some extra clauses saying I make a new variable z2 and it has to be equal to the and of x3 and not x4 in this case. And then I'll drop in z2 there, right? And then we can make a new variable z3 for this subtree. Okay, I'm kind of running out of space. So I can bring this down and say, okay, z3 needs to be equal to the and of z1 and z2. Again, we know how to express that, or we'll derive that in a moment. And then I kind of drop in z3. Okay, and little by little, I'm eating away at this tree. Okay, and that was only ands, but that would also work for ors. So maybe this subtree on the bottom is an or. I'd introduce some z4, right? And I would say, I would put z4 there and stuff like that. And this way the tree kind of disappears, and I just have this conjunction of all these mini clauses. Z1 and Z4 are what? Yes, that's okay. So at the end, what will happen is that, well, I'll draw it out in a second, but this will come out. This will turn into like the and of two ors or three ors or something, right? It'll be some conjunctive normal form. So each of those little assignments will be some small conjunctive normal form, small conjunctive normal form, small conjunctive normal form. And I'll combine all of them by saying this conjunctive normal form and that conjunctive normal form and that conjunctive. I'll glue them all together with more ands. I have it drawn out. So, okay. All right, so that's the idea. We're going to leverage assignment, okay, and introduce variables. So if I wanted to write x1 is equal to x2 and x3 in conjunctive normal form, right? I guess we can like plug in our formula, right? So we would get something like x1 or the negation of x2 and x3, something like that. Okay, so I drew a line above the whole clause. And x1, oh no, I got it wrong. x2 and x3, or not x1, right? So this is not in conjunctive normal form right now, but we can gradually work with this. So let's see, what does this become? Let's just do one clause at a time first. So if I wanted to deal with that, then what? You get something like x1 or not x2 or not x3, something like that. And these nested parentheses can be deleted. Correct me if I do it wrong, because this is absolutely where I'll do it wrong, right? All right, and then the next one, I guess we can do some distributing. So we can do like x2 and not x1, or x3. Oh no, I did this wrong. Would it be the or? You guys just tell me if I'm doing this right. Is that correct? Maybe. Okay, hopefully it's correct. It looks like these outer parentheses can be removed. So I'm left with an and of ors. So now I have a conjunctive normal form. Okay. I don't know if you guys want me to work through the other one, but we can do the same thing where I plug in x2 or x3 into the formula and just do a little bit of Boolean algebra and come out with some constant size conjunctive normal form. Okay. All right, so right, we can apply that to this tree, which I did. Okay, so all right, don't ask me how long this took me, right? But I've sort of introduced variables for all those intermediate nodes, all those intermediate operators. And then I just listed all of the clauses that get output based on the whatever formulas, okay? And I would glue all of these together, by making it one big conjunction, okay? Now, okay, one thing that is important is that the size doesn't get too big, right? How can I argue that the size didn't get too big? No, that's not why. I want to argue that the formula I produce, because this is somewhat bigger, right? I mean, this thing on the bottom here is a little bit bigger than the original thing. But we need to really argue that whatever I produce on the bottom is like within a polynomial factor of the original formula. How can I try to argue that? Yeah. Oh, but one thing we have to worry about, for example, is that if you did it like to a tree, so like it kind of like doubles and then doubles again and doubles again, that's where you get an issue where you might get like an exponential growth. If that makes sense. Yeah. So why aren't we getting an exponential growth here? Every variable is connected to a maximum of. Well, okay. All right, let's start first. How can I argue that the number of variables I introduce isn't too much? That's a slightly simpler question, right? How do I argue that I only introduce a limited number of new variables, not exponential in the original size? Okay, so there's only one variable per node in the original formula, right? And each node corresponds to like a matching set of parentheses. So the number of variables I introduce is not more than the size of the original formula. Okay. All right. Now, how do I argue that the entire formula I produce is close to the size of the original formula?
I'm not sure, but
You can say that each node will only generate 3.
Yeah, so each of those nodes, each of those intermediate nodes only, generated 3 of these clauses, which has like, at most 10 variables or something going on, right? It's a short line. Okay, so each of those intermediate nodes, which is like an outer parentheses in a formula, led to maybe 3 clauses and 20 total symbols in the output formula. So really only increasing by a factor of 10 or 20 or some constant. Okay, but we need to introduce variables to be able to pull this off. Okay. All right. Okay, so that's the construction. That's our polynomial time. I mean, you can imagine coding this. I'm not worried about doing it super fast. All that really matters for this theorem is to be able to do it in polynomial time, so just take your time and do it correctly. Work bottom up and stuff. But we've shown how to create this formula of roughly the same size and preserve satisfiability. The trick is just to use the assignment operator, and so that's how we complete the overall theorem. Any questions? It's like kind of grungy, but it's also like some big ideas. The idea of relating problems is a big idea. Okay. All right. Okay, so you can keep playing this game, right? So CNF was also hard. So let's make it even more special. So 3SAT is a special case of CNF where each clause has exactly 3 variables in it. So I'm really kind of trying to limit things. All right. So who thinks that we can do a polynomial time algorithm for 3SAT? 1, 2, 3, 4. All right, like 6 of you. And who doesn't think we can do an algorithm for 3SAT? Or like we'll get some logjam like before. Okay, 12, 20. And then who wasn't planning to vote the entire time? Okay, mildly honest. Okay, so, right, so is there a polynomial time algorithm for 3SAT? And again, we don't have an algorithm for 3SAT, but we have one of these, ties, okay? We can prove that there's a polynomial time algorithm for Boolean SAT if and only if there's a polynomial time algorithm for 3SAT. Okay. All right, how would we prove this? How do I prove such a thing? Same thing. So yeah, what's the same thing? Yeah, you can try to convert any Boolean formula to 3SAT. Although if you want it to be even lazier, given what we have just done, it suffices to be able to convert any CNF formula to 3SAT, right? Because we already know CNF is just as hard as Boolean SAT. So you can take advantage of these kind of connections you've already made. So, okay, so, right, we can show how to convert any CNF to 3SAT, right? And so really the only difference between what CNF and 3SAT is you have to really worry about the big clauses that have like 10 variables in it. And you have to get that down to 3, right? So if I had, let's say I had 4 variables, right? That's not a 3SAT. I need to convert this into 3 variables or groups of 3, right? How could we do that? Okay, we can introduce Z1 is equal to X1 or X2. Z2 is equal to X0 or X4. And then we have some kind of Z1 or Z2, so to speak. All right. The other issue you have to deal with is how do you deal with variables of size 2? Yeah, we can add some like bogus variable, and then we can try to set up something so that it cannot be true. So, so that it always has to be false, right? So okay, then you have to make some kind of gadget or something. Okay, all right, but the point is that at some level, some kind of proof ideas, you play some games and you can show that, okay, 3SAT is also hard. All right, so 3 doesn't help. All right, let me, well, we're going to finish early probably. Okay, let me give one more example. Okay, so we discussed this a little bit earlier. We're doing topological sort. This is circuits, right? So the only difference is that with these Boolean formulas, that always comes out as a tree. But circuits, like those intermediate nodes, can kind of depend on each other in more complex ways, as long as it forms a DAG. Okay. So, right. So, for example, that's a circuit for addition, and it's a little bit smaller than we had the tree for addition because it can kind of reuse some computation. Okay. All right. So I don't know. I'll just remind you guys. Yeah. Okay. You guys all know this from last time. All right. So as you might imagine, yeah, we can also have a question for circuit sat, right? Given a circuit, decide if it's satisfiable, right? Okay. All right. We'll take the same vote as always, right? Either you think we can come up with an algorithm, you don't think we can come up with an algorithm, or you're not going to vote. All right. Who's not voting? Yeah. Isn't circuit sat? Well, so the earlier versions of sat, there were always Boolean formulas. So all circuits can't necessarily be expressed in Boolean formulas. So anything with nested parentheses looks like a tree. But a circuit, these circuits, these aren't trees, right? Because, like, just look at these four across. It just forms a DAG, so it's more general. Yeah, is it more? Yeah, good question. Is it more general than Boolean formulas? It is, right? So every Boolean formula is a DAG because a tree is a DAG. Just not very interesting because there's not much cross connections. Sorry? Can you split a circuit into trees? So the interesting question is, can you take circuits and convert it into Boolean formulas? All right, that's a good question. All right, so who thinks that we can take any circuit and convert it to a Boolean formula? Okay, and who doesn't think we can do that? Okay. All right, then how do we convert a circuit to a Boolean formula? How do I have a circuit like this thing and convert it to a Boolean formula? Sorry? You can duplicate inputs. Sure. Well, I'm looking for a more precise answer because we also want to argue that the size of the Boolean formula is going to be similar. Okay, I'm really interested in converting a circuit to a Boolean formula of roughly the same size. So duplicating seems to at least run the risk of things blowing up quickly if we're not more careful about it. How would I turn this circuit into a Boolean formula systematically? Oh, we can use assignment operators again, right? So these are just nodes like before. I'll call this Z1, right? I'll call this Z2. I'll call whatever this Z3, right? And I can still take the DAG, the circuit, and just rip off parts by assignment, okay, and combine the whole thing. So actually the same construction as before. Okay, so we end up with the same theorem. That there's a polynomial time algorithm for Boolean sat if and only if there's a polynomial time algorithm for a circuit sat. Okay. All right. So, right. So that's the algorithms lecture with no algorithms in it to some extent, right? We would really like, because these are kind of pretty basic problems, right? I mean, circuits are in computers. Real questions can be expressed in Boolean logic, right? We really would like to get algorithms for any of these problems, right? And we don't have algorithms, and people are still looking for algorithms. right? People do care about this. But we do know, so we can't solve them, but we do know that they're kind of equivalent as far as this question of whether or not there's a polynomial time algorithm. Okay? So this is sort of it's still answering questions of relevance to people who want to make algorithms, who want to use algorithms. But it's sort of looking at the other side of the coin, right? This is a situation where I don't know how to solve a problem. I don't know how to solve several problems, right? And at some level, if I focused on one problem in isolation, I might never come to a resolution. But with a slightly different style of thinking, by using reductions, right, converting one problem to another, I can at least relate the questions to each other, right? So we've kind of taken 4 impossible questions, and while not answering them directly, we have learned something about these problems. We understand that they're kind of equivalent. I understand that, oh, if I wanted to work on a really general circuit SAT, I could focus on the cleaner 3-SAT problem, right? And maybe look for some structure or something from that limited setting. There might be some tricks that work or something. Okay, so this is a different style of thinking, which will really kick in when we come back after the midterm. We'll start encountering problems that some of those tricks we've learned in the past few weeks don't work. Okay, and sometimes they do. And there's 2 questions going on. Can we distinguish one case from the other? Right? When there is an algorithm, can we come up with an algorithm using especially the techniques from the past few weeks? And if we can't find an algorithm, can we at least come up with some explanation by trying to tie it with another problem that we think is pretty hard? So at least I can feel good about not solving that problem, right? Which is really much more realistic as to what happens when you encounter a problem in the wild, right? If I give you a problem on the homework, especially the first few homeworks, you know there's an algorithm because I picked out the problem, right? But in the real world, maybe there's problems we don't know how to solve, right? So we're going to expand our thinking a little bit, especially after the midterm. Okay, that's all I have for today. And yeah, see you guys and good luck.